Welcome back, everybody. So in this lecture, we're going to be talking about how to solve a exponential and logarithmic equation. And the general strategy for solving an exponential or logarithmic equation is pretty much the same strategy for solving any other equation. You're going to simplify, and then you're going to invert, then you're going to solve. So before going into details regarding exponentials and logarithmic equations, let's talk about the different types of exponentials and logarithmic equations. So the first type of exponential logarithmic equations you're going to have is one where you have an exponent on one side of the equation equals an exponent on the other side of the equation, or a logarithm on one side of the equation equals a logarithm on the other side of the equation. And how we're going to treat those equations is different than when we're going to have equations that look something like this. So when we have equations that look like this, we're going to have another strategy entirely. We're going to have to do a mixture of exponents and logs. But before we get too in depth with this type of equation, let's go into some theories behind how we solve exponents and logarithmic equations and why they are done this way. So remember our discussion about functions. We said that a relationship or an equation is a function if it meets a certain set of criteria. Those criteria being that for every input, there's an output, that not all outputs in the range may be achieved, multiple inputs may have the same output. However, one input cannot have multiple outputs. And if those criteria are met on an equation, then it is a function. And notice, why do we want a function? We want a function because it allows for predictability. We know before we plug in our x what our y will be, or we can predict what our output will be given an input. And then we talked about invertible functions, functions that have an inverse. And before a function can have an inverse, it must first be a special type of function, namely a one-to-one function. And a one-to-one function has the same characteristics as every other function, but remember that criteria that said multiple inputs can have the same output? That is not true for a one-to-one. For one-to-one functions, one input must have one unique output. So every input has its own unique output. And that way you know based on the output what the input is. Well, what do I mean by that? So let's take a mapping of a function. Now, this is a function because every input has an output. Not all outputs are achieved. Multiple inputs may have the same output, but no one input has multiple outputs. Now, it is a function, and it allows for predictability. I know if I input A into this function, I'm going to get 1. If I input B, I'm going to get 1. And if I input C, I'm going to get 3. But there's a problem. I can predict in the forward direction. Okay, I can predict based on my input what my output will be. However, I do not have the same predictability in the reverse direction, meaning that if I look at my output, I don't know particularly what my input is. Well, to a certain extent. If I look at my output and I know it's 3, then I know my input was C because 3 has a unique input that gives it. Okay. However, if my output is 1, I don't know whether that output came from an input of A or an input of B. And so even though this is a function, it does allow predictability, meaning that I know based on my input what my output will be. It doesn't allow me reverse predictability, in which means that based on my output, I don't know what my input is. I know based on my input what my output is, but I don't know based on my output what my input was. Now, let's look at a mapping for a one-to-one function. A one-to-one function looks something like this. Okay, do you see the difference? In the previous mapping, we had A and B mapped to 1. So we knew if we put in A or B that our output would be 1. But in this, every input has a unique output. Okay, every input has a unique output. So if I input A, I know I'll get 1, B, I'll get 2, C, I'll get 3. And what this one-to-one function allows me to do is look at my output and also know what my input was. That if I have an output of 1, I know that came from an input of A. And if I know I have an output of 2, my input was B. And if I had an output of 3, my input was C. So this is the type of function that must exist one-to-one in order for you to have an inverse. And the inverse is the reverse function. So if a function is the forward direction, the inverse of that function is an equation that goes in the opposite order, where my input is the actual output and my output is my original input. And we've talked about this, and we said that just like there is a vertical line test for functions, that one-to-one functions have also a similar graphical test, namely the horizontal line test. And that given a graph of a function, if I can draw a horizontal line and it only crosses that graph once, that is a one-to-one function. Now, this characteristic is important. And if we notice the graph of our exponential and logarithmic functions, they all pass not only the vertical line test because they're functions, but they also pass the horizontal line test as well. And that's why exponentials have an inverse function, and that inverse function is a logarithm function. Now, this very characteristic, this one-to-one characteristic is what allows us to be able to solve basic exponential and logarithmic equations. And the one-to-one property says that if I have two exponentials, okay, a to the x and a to the y, if I say a to the x equals a to the y, then it must be true that x equals y. So let's put some numbers in it. So let's say, for example, I have an equation 2 to the x equals 2 to the 4th, okay? Well, what does that mean? That means that x equals 4. So the easiest way to solve an exponential or a logarithmic function is make sure that if you're dealing with exponentials, both sides of the equation have the same base for their exponent. And if you're dealing with logarithmics, that both sides of the equation have the same logarithmic base. Okay. And I'm going to show more about this in a second. Examples like this. So let's say I, for example, have a problem like this. Okay, 3 to the x equals 27. Well, the easy way to solve this equation is to say, okay, is there any way I can rewrite 27 using base 3? And the easy way to write 27 using base 3 is that 27 is 3 cubed. Okay. Now, based on my one-to-one property, if 3 to the x equals 3 cubed, that must imply that x equals 3. And these types of equations can get pretty elaborate, okay? These types of equations can get pretty elaborate. So let's say, for example, I have something like, say, 2 to the x plus 1 minus 1 equals 15. Okay, so step 1 is to isolate. That means get the exponential by itself. Okay, so that's going to be the key going forward for all of my exponential or logarithmic functions. Before I can do anything with the exponent or logarithm, I got to get it by itself. So the first thing I'll do is add 1 to both sides. And that'll give me 2 to the x plus 1 equals 16. Then I ask myself, okay, well, can I rewrite 16 using base 2? And I can't. 16 is 2 to the 4th. Now, 2 to the x plus 1 equals 2 to the 4th. That must imply that x plus 1 equals 4. And then we solve for x by subtracting 1 from both sides, and we get x equals 3. Another level of this would be something like this. Three times 2 to the 2x plus 1 plus 2. So again, first step is to isolate this guy. So we're going to subtract 2. Remember, we add and subtract whatever's around it, then we multiply or divide. So we subtract 2 to both sides. We get 3 times 2 to the 2x plus 1 equals 24. Now, we have 3 times 2 to the 2x plus 1. So this is my exponent. This 3 is not a part of my exponent. So I have to get rid of it. So I divide both sides by 3. And I get 2 to the 2x plus 1 equals 8. Okay. Now, I then ask myself, okay, well, can I rewrite 8 using base 2? And you can. 8 is 2 cubed. Now, what does this say? 2 to the 2x plus 1 equals 2 cubed, which means the exponents have to be equal, and then you solve. All right. So take home point for basic exponential equations, you get the exponential portion by itself, isolate it by getting rid of whatever's being added or subtracted and whatever's being multiplied to it. And then you see if you can write the other number in the same base as your equation, set the exponents equal to one another, and solve. Okay, so say, for example, we have a problem like this. Common log x squared equals common log 2x plus 3. Okay. Well, we use the one-to-one nature of common logs. So that means x squared is equal to 2x plus 3. Okay, and we can do this because the logs have the same base, and in this case, they both have base 10, common log. And this is a quadratic type problem. So how do we solve that? We get everything to one side, so the other side equals 0. Right? Now, we can solve this by factoring. So x minus 3 times x plus 1 equals 0. And solve each one. So my solution set here is -1, 3. Now, since this is a quadratic type equation, the thing that we have to be careful about is we have to check to verify that each equation gives me a true statement, okay? So when we plug in -1, so log -1 squared is 1 equals log -2 plus 3 is 1. So that works. Now we got to try 3. Okay. So log 3 squared, which is 9. 2 times 3 is 6, plus 3 is 9. So 3 works. Okay. So both answer options are correct. And if you have a quadratic type problem with 2 or more results, you have to check and verify each one is a true statement. Moreover, remember, what is the property of my logs? Remember, this portion cannot be negative. So if I end up getting an answer that makes this portion of my logarithm negative, I have to throw that answer out. Okay. So when I go back and check, number one, I got to make sure both sides equal each other. So in this case, log 1 equals log 1 or log 9 equals log 9. And moreover, I have to make sure that all of the laws of logarithms are upheld. That means what you're taking the log of cannot be negative, right? Now, those equation types will be equation types that are a little bit easier in nature. But for the most part, you will not get equations that are like this. So you may get an equation like this. You may get something that says 3 to the x equals 7. And there's a dilemma in this. There is no way I can rewrite 7 using base 3. There is no exponent that I can raise 3 to get 7. No, at least no integer exponent, okay? So what do? Well, in order to solve equations of this type, we're going to have to understand the inverse nature of exponents and logarithms. So what do I mean by that? Well, let's take, for example, 3 to the x, okay? Or the exponent 3 to the x. The inverse of this is log base 3. Okay. And likewise, if I have, say, natural log or log base e, the inverse is e to the x. Okay. So remember when you're solving equations of the general type, when you got an answer like this, what did you do? Well, yeah, you divided by 3. And why did you divide by 3? Well, because 3x means 3 times x. So you're saying 3 times some number equals 9. So in order to find what x is, you have to do the inverse of multiplication, which is division. So instead of multiplying by 3, you divide by 3 because that's the inverse of multiplication. And if you had a problem like this, what did you do in order to finally solve for x? Well, you multiplied both sides by 2. And the reason you multiplied both sides by 2 is because x over 2 is x divided by 2. And in order to find x, you had to do the inverse of division, which in this case is multiplication. And in that same theory, we're going to do a similar inverse relationship, or use the inverse relationships of exponents and logarithms to find the solution. So let's go back to the original problem. 3 to the x equals 7. Now I've established the fact that there is no integer exponent that I can raise 3 to get 7. So what do? Well, the inverse of 3 to the x is log base 3. So what I'm going to do is I'm going to take the log base 3 of both sides. Okay. Now, remember my identity that log base a of a to the x is x. Okay, so the log of an exponent a is just x. Okay, remember they undo. So log base 3 of 3 to the x, the log 3 and 3 cancel, and that just leaves me x. X equals log base 3 of 7. And you can plug this into your calculator and you'll get an answer. But for my purposes, I would like an exact answer, so you can leave it like this. Now, remember your change of base forms. This is also, you can also rewrite this as the natural log of 7 over the natural log of 3, or you can rewrite it as the common log of 7 over the common log of 3. Okay. My purpose is, since it's going to be a multiple choice test that I will give you with these problems, I will give you an answer that looks something like this. All right. Now, what if we have the reverse? Log base 6 of x equals 3. Okay, log base 6 of x equals 3. Well, how do we solve this? So remember the property log base 2 of x, 2 to the log base 2 of x is x. Okay, so they cancel out. So I'm talking about these two properties right here. So in the previous problem, I used this property, and in this problem, I'm going to use this property. Okay, they cancel out. So this property, log 2 to the log base 2 of x cancels out. So I have this situation right here. Log base 6 of x equals 3. So how do I do the inverse of log base 6 of x? Well, I make everything an exponent of 6. So I make everything an exponent of the base of the log. Now, based on my properties, 6 to the log base 6 cancels. That leaves me x equals 6 cubed. And if my calculations are correct, 6 cubed is 36 times 6, which is 216. Right. Now, let's look at something like letter C. 5 minus e to the x equals 0. Now, like in any other equation, you got to get e to the x by itself. Okay, you got to get the exponent portion by itself. So I can move 5 to the other side and get negative e to the x equals negative 5. But I'd like to keep my exponent or my logarithm positive. So instead of moving 5 and dealing with a negative exponent or a negative exponential function, I can move e to the x and get e to the x equals 5. So now this is an exponential equals 5. Okay, well, if I have an exponential equaling a number, how do I undo the exponential? I take the log of it. But what is log base e? Well, remember, log base e is one of our special logs, the natural log, ln. So we do the natural log of both sides. Okay. And remember log base e of e, so the log base of an exponent, they cancel out. That's x equals the natural log of 5, which is some sort of not imaginary, irrational number. So take home point, if you have a exponent equaling some number, you're going to do log base a of it of both sides to cancel and get the variable by itself. And if you have a logarithm equaling a number, then you're going to make everything an exponent of the base to get the variable by itself. Okay. So these are one of the two strategies you're going to use. That's if you can't make everything the same base. Okay. So you're going to try to make everything the same base, but sometimes there is no way you can rewrite a number using integer bases. And then you're going to do something like this. So try to make it the same base. If it doesn't work, you have to use either this strategy or this strategy, okay, depending on what you end up with. But the first step is to get either the logarithm or the exponential portion by itself, by getting rid of whatever is being added to the logarithm or exponent and getting rid of whatever is being multiplied or divided to it as well. So let's look at D. 9 to the x equals 1/3. Now, I can't make 1/3 a power of 9. There's no way I can rewrite 1/3 and have it be 9 to some power, okay? However, I can do a little trick. I can look at both of these things and say, okay, well, both of these guys can be rewritten using base 3. 9 is 3 squared. 1/3 is 3 to the negative 1. Okay, don't forget about my fractions with negative exponents. Okay, so 9 can be rewritten as 3 squared to the x, and 1/3 is 3 to the negative 1. Now, remember my properties of exponents. What happens when I have an exponent raised to an exponent? Yes, you multiply. So this is 3 to the 2x equals 3 to the negative 1. Now, since they both have the same base, set the exponents equal to one another and solve. Now, I know what you're going to say. Professor D, there is absolutely no way I can see that. You can if you practice, okay? Remember, if you're dealing with exponentials, see if one can be written as an exponent of another. So see if one side can be rewritten using exponents. Or see if the bases of both sides have a common base. Okay, so for example, 9 and 1/3, they have a common base of 3, and I can rewrite both 9 and 1/3 using base 3. Okay, so that's what you have to look for. There is no way you can do that. Like in the beginning of this lecture, I talked about 3 to the x equals 7. There is no common base between 3 and 7. Then I have to use my inverses, either logarithms in this case, or if I was given a logarithm, exponentials. So in the slides on Blackboard, this is the basic strategies you're going to use. Number one, at all costs, if possible, rewrite the original equation in a form that allows for you to use the one-to-one properties of exponentials or logarithmic functions, which means try to make everything to have the common base or a common power, and then set the exponents equal to one another or set the bases equal to one another, okay? And if not possible, then you have to either use the inverse properties of exponents and logarithms. If you're given an exponential and you can't find a common base, you have to take the log, base a of both sides. And if you're given a logarithm, you have to take the exponential of both sides. And this is strategies that you will use once the exponential or logarithm is by itself. So first you have to simplify. That means isolate. You have to get rid of whatever is around the exponential or logarithm portion of the equation. Now I know all this seems like a lot to digest at one shot, but we're going to do a couple of example problems and it's going to make sense. So let's look at e to the 2x equals e to the x squared minus 8. Okay. Now this is sort of done for me, right? Both are common base e, so I can just set 2x equal to x squared minus 8. And this is a quadratic, so I can have to bring everything to one side so that the other side equals 0, so that I can factor. Okay. So what are two numbers that multiply to give me -8, but combine or add to give me -2? That would be -4 and +2. So x equals 4, x equals -2. So my solution set is -2, 4. And you can go back and verify that they both give you a valid, both sides of the equation will be the same. Okay. Now B, 2 times 5 to the x equals 32. So before I can do anything, the first thing I got to do is divide both sides by 2. Because I got to get my exponential by itself. Okay. So 32 divided by 2 is 16. Now I have 5 to the x equals 16. Well, what do I do? Well, I'll first try to see if I can rewrite 16 as using a base 5 and some exponent. But there's no way I can rewrite 16 as a power of 5. Okay. So 5 to the first power is 5, 5 to the second power is 25. I will not get 16 rewritten as 5 to some exponent. So since I can't make both sides have a common base, I have to use the inverse of my exponential with this logarithm. So I will do log base 5 of 5 to the x equals log base 5 of 16. So I'm going to do log base 5 of both sides. Now log base 5 of 5 to the x is just x equals log base 5 of 16. And you have to understand, this is a number, okay? If you plug this into your calculator, you will get some sort of decimal value, okay? So this is some irrational number, but it is a number, and that will be your solution. Okay, so let's look at this one. 6 times 2 to the t plus 5 plus 4 equals 11. Okay, so pretty involved. So the first thing I'm going to do is get my exponential, which is this portion right here, by itself. So the first thing I got to do is get rid of whatever is being added or subtracted to it. So I got to get rid of the 4, so I'm going to subtract both sides by 4. Now, my exponential is still not by itself, so I'm going to divide both sides by 6. Okay. Now, obviously, I cannot rewrite 7/6 as 2 to some exponent. Okay, so I'm going to have to use the inverse of the exponent of 2 by taking log base 2 of both sides. Okay. This cancels. That gives me t plus 5 equals log base 2 of 7/6. Now, I solve for t. So t equals log base 2 7/6 minus 5. So if you plug this into your calculator, you'll get a number. Now remember, we were doing expansion and contraction of logs in the last section. Remember how I can rewrite log base 2 of 7/6 and what the quotient rule of logarithms said. It said that I can rewrite log base 2 of 7/6 as log base 2 of the numerator minus log base 2 of the denominator. And that would be my answer. Okay, so this is the next problem, and they can get pretty involved. Now remember, before I can do the inverses of logs and everything, inverse using logarithms or whatever, I have to get the exponential portion by myself. But there's a problem here. I have this as an exponential and this as an exponential. And there's no way I can combine e to the 2x and e to the x, okay? E to the 2x minus e to the x, I can't do any of that, okay? So remember, I can multiply exponents when, I can add exponents when the bases are being multiplied and the bases are the same. But there's nothing I can do to the exponents if the bases are being added or subtracted, okay? Can't do anything. So how do I deal with this? Well, these types of problems where you cannot isolate and make into one exponent multiple exponentials because they're being added or subtracted are known as quadratic type exponentials. And we're going to do a little bit of a trick. Okay, and the trick is, well, e to the 2x is the same thing as e to the x squared, or e to the x to the second power. Because remember our properties of exponents. When I have an exponent raised to an exponent, I can multiply that. So e to the 2x is e to the x squared, or e to the x to the second power. So let's rewrite this and see if this helps us. Now, initially you'll be like, okay, well, that really didn't get me anywhere. It just made him look worse. Well, this does, if you look at it in a different way, this sort of does help us. And the way we do this is called substitution. I can replace e to the x with another variable. So I'd say let the variable a equal e to the x. Okay. And wherever there's e to the x in this equation, I'm going to replace that with a. And there's nothing in math that says I cannot replace a variable with another variable. So all I'm doing is I'm replacing e to the x with the variable a. So that becomes a squared minus 7a plus 12 equals 0. Now, I should know what to do with this. This is a quadratic equation, and I know how to solve a quadratic, okay? Thankfully, this one side already equals 0, so all I have to do is factor. Two numbers that multiply to give me 12, but add to give me -7. That's a minus 3, a minus 4 equals 0. And so when I solve this, I get a equals 3 and a equals 4, okay? But there's a problem. I solved this equation for a, but that wasn't my objective. My objective was to solve for x, okay? But I know a is e to the x, so that means I go back and replace a with e to the x, And these are two mini exponential equations. So how do I do this? How do I solve for x here? Well, I take the logarithm, the inverse log, and the log, I'll do the log base e, which is natural log. So if I have an exponential, I got to take the log of both sides, okay? Log of the same base. And this is log base e, which is known as natural log. Okay. The natural log and e cancel. That gives me x equals the natural log of 3, and x equals the natural log of 4. So my solution set are these. So when you have multiple exponentials in the same problem and you cannot consolidate and make them into one exponential because they're being added or subtracted, you may have to employ what we call the substitution property, because this is known as quadratic type exponential equation. Okay. And there are a couple like this in your homework packet and in your practice problems as well. And you will have a couple of these on the test. So up to now, we've been dealing strictly with exponential types equations. We've hinted on logarithmic type equations, but more or less concentrating on the different types of exponential equations you'll have. And logarithmic are done the same way. You get the logarithmic portion by itself, and then you do the inverse of log, which is making everything an exponent. Okay, so if you look at this problem type, the logarithm is by itself on one side of the equation, everything else is on the other side. Now we're going to do the inverse of logarithm, which is making everything an exponential of the base of the log. Well, this is natural log. And natural log, again, to remind you, is log base e. So we're going to make everything an exponent of e. So we took e, we made everything an exponent of e. That's what we did here. And here, e to the natural log cancels out, gives me x. And my answer is x equals e cubed. And this is the general strategy we're going to use for logarithmic equations. Now, remember in the last section we talked about condensing or contraction of logs? Well, this is where it's going to come into play. So if we have multiple logarithms on the same side, we're going to have to do our properties of contraction, or either our quotient rule, product rule, or power rule, and rewrite all of those multiple logarithms as one log. And you're going to see that before we take the inverse. So here are a couple of example problems. I would pause the video to see how they did these problem types. And then we're going to walk through a couple of problems together. Okay. So let's start off easy. Let's start off with A. The natural log of x equals 2/3. Okay. Well, we're fortunate enough in this problem to have the natural log isolated. There's nothing around that logarithmic expression. So all we have to do is the inverse of the logarithm, which in this case is e. Okay. The exponent and the log cancel, giving me x. So my answer is e to the 2/3. Right. Let's look at B. Log base 2 of 2x minus 3 equals log base 2 of x plus 4. Now, it is important to know that when I write logarithms, I have to write it in parentheses because I have to indicate what I'm taking the log of. So when I have parentheses, whatever's in parentheses is the entire expression that I'm taking the log of. However, If the same thing was written as this expression and this expression mean entirely different things. This is saying I'm taking log base 2 of 2x minus 3. Here, this is saying I'm taking log base 2 of just 2x. Minus 3 is like on the outside, okay? It's being subtracted. 3 is being subtracted to log base 2 of 2x. So if there's no parentheses, it's understood that whatever I'm taking the log of is the number or term directly in front of the log. So here, I'm just taking the log base 2 of 2x. If I have parentheses, then whatever's in parentheses is part of the entire logarithm, okay? So here in this original question, I'm taking log base 2 of the entire 2x minus 3. So the reason this is important to know about parentheses is because the way you would approach this problem will be a little bit different than the way you'd approach this problem. So let's go back to the original equation. Log base 2 of 2x minus 3 equals log base 2 of x plus 4. Well, I'm fortunate in this regard because both sides of the equation have the same log, or having log base 2 done to it. So we're going to use the one-to-one property, saying that if log base 2 of 2x minus 3 equals log base 2 of x plus 4, that must imply 2x minus 3 equals x plus 4. Okay. Since both sides are log base 2, I can set whatever's inside the logs equal to one another. And now it's just a matter of solving like I normally would. I would subtract x from both sides, and I would add 3 to both sides and get x equals 7. Okay. Now, let's look at C. Common log 4x minus common log 12 plus x equals common log 2. Well, we want to find a way of getting the logs by themselves, okay? On the left side, we want a way of rewriting this as one logarithm, okay? So we have a log of something equals a log of something, and then we can just drop the logs. Well, this is where the properties of contraction come into play. So do you remember, how can I contract log base 4x minus log 12 plus x? I have to use my quotient rule that says log of 4x minus log of 12 plus x is the same as log of 4x divided by 12 plus x equals log of 2. Now, since I'm doing common log on both sides, I can drop the logs on both sides and get 4x over 12 plus x equals 2. Now, remember, how do we solve this? Okay, we can cross multiply and get 4x equals 2 times 12 plus x. Okay. Remember, you can write any whole number as a fraction by putting it over 1. You cross multiply. Now it's a matter of just solving. 4x equals 24 plus 2x. Subtract 2x from both sides. Equals 12. So you have to approach each problem on a case-by-case basis, depending on what you've been given. Sometimes you can drop the logs because you're taking the same log on both sides of the equation. Sometimes you have to condense. Sometimes you have to do the inverse. And it's totally dependent upon what you've been provided in your problem. Okay, so let's look at this problem. 7 plus the 3 times the natural log of x equals 5. Okay. So the first thing we're going to do, we got to get the natural log by itself before we can invert it. So we're going to subtract 7 from both sides. Then we're going to divide by 3. Okay. Now, something to pay attention to. Say, for example, you had a problem like this. Okay. What would be your answer? Well, your answer should be no solution. Because remember, the domain and range of my exponent versus my logs. In the for my exponential functions, domain x can be all real numbers, but the range is strictly positive from 0 to infinity. So here, -9 is my output. Okay, 2 to the x equals -9. I can't have -9. Okay, I can't raise x. I can't raise 2 to some power and get a negative result. So there is no solution for x that I can plug in for. There's no number I can plug in for x that would result in a -9. So there would be no solution. And however, this is different. And this is, well, this is because remember the range, the outputs cannot be negative for an exponential. However, in a logarithm, remember the domain and range values are flipped. So the domain is all positives, but the range can be all real numbers. Okay, range can be all real numbers. So the number on the opposite side can be positive or negative. It's just that the domain, what's inside here, can't be negative. Okay. So again, to say again, the output for for an exponential, it can't equal a negative. But for a logarithm, I can have a negative. The only thing I can't have a negative in a logarithm is what I'm taking the log of. So keep that in mind. It's pretty important to know. So natural log of x equals -2/3, and that's fine. I can still do this. So I have to invert log, natural log. So natural log is log base e, so I make everything a power of e. So e and natural log cancel, and that gives me x equals e to the -2/3. And sometimes we do not like leaving our answer with negative exponents. So remember what a negative means. It means take the reciprocal of the base. Let's look at this problem. 3 times the natural, 3 times log base 4 of 6x equals 9. So again, my first thing to do is to get my entire log by itself. Okay, so I'm going to divide both sides by 3. And now I have to invert. Well, how do I invert log base 4? Well, I make everything a power of 4. Okay. 4 and log base 4 cancel. That leaves me 6x equals 4 cubed. And 4 cubed in your calculator should give you 64. 4 times 4 is 16. 16 times 4 is 64. So 6x equals 64. X equals 64/6. We can reduce 64/6 because both the numerator and denominator are divisible by 2, and that gives me 32/3. Final example type. Log x plus log x minus 9 equals 1. So remember what our log is. What's the base of our log if no base is indicated? it is log base 10 because this is common log. So the first thing we're going to have to do is get log by itself and in one expression. So how are we going to do that? Well, we have to combine this or condense it. Okay, remember, before we can take the inverse, we have to make it into one logarithm. Well, how do we condense this? We use the product property or product rule of logarithms that says log x plus log x minus 9 is the same as log of x times x minus 9. Okay. Now, logs by itself, now we have to invert it. So what is the inverse of log of the common log? Well, it's base 10. So I make everything a power of 10. Okay. 10 and log cancel. That gives me x times x minus 9 equals 10 to the 1, which is just 10. So how do I solve this? Well, we first are going to distribute my x. And then we realize that this is a quadratic equation that in order to solve, I have to move everything to one side so that the other side equals 0. Factor. Two numbers that multiply to give me negative 10, but add to give me negative 9. That's x minus 10, x plus 1. So my solutions are 10 and negative 1. Now remember, what did I say? Whenever you have two solutions from a quadratic type problem, you have to go back and check to see if both sides work and if the solutions uphold the laws of logs, namely that this portion can't be negative. And we see immediately that if we plug in negative 1 for x, we get log of negative 1 plus log of negative 1 minus 9 equals 1. Well, that's a problem. I can't take the log of negative 1. This does not exist. And this becomes log of negative 10. And again, this portion does not exist. So having x be negative 1 violates my properties or rules of logs. So I have to eliminate that answer. So negative 1 is not an acceptable answer. It's known as an extraneous solution. It's a solution that does not work. So that means my only true answer is x equals 10. Okay. Well, I know I threw a lot at you tonight regarding all of these equations with exponents and logs and inverses and one-to-one property and contraction. It's a lot to digest, quadratic type exponential equations. But you have ample practice problems in your practice packet and in your study guide, and I highly suggest you practice them. And I will probably upload another video that will go through different problem types so that you can see how we approach each individual type. Main take-home point is each problem, whether they're exponential or logarithmic in nature, need to be approached on a case-by-case basis. Okay, there's no cookie-cutter way of doing it. Take home, first get either the exponential or the logarithmic by itself by getting rid of whatever is being added or subtracted to it. And then if you are dealing with logarithmic equations, make sure that it is one log. Okay. Then go down the properties. If it's an exponential, see if you can rewrite both sides of the equation so that they're like the same base. And if not, then you have to do the inverse of exponentials, which is log. And if it's multiple logarithms, you have to use your properties of logarithmic contraction, like the product rule, the power rule, and the quotient rule to write it as one log before you take the inverse. And if you have multiple exponents, you may have a quadratic type exponent. Make sure that the answers you get coincide with the properties of logarithms. namely that the inside of the log cannot be negative. So this portion can't be negative. Also, if you have an exponential, something like this, if an exponential equals a number, that is a no solution, because an exponential cannot equal a negative. So the exponential cannot equal a negative, and a logarithm you cannot take a negative of a logarithm. So logarithms have to be positive, exponentials have to equal something positive. Again, I stress practice. It will come. Initially, it will be a little bit challenging, but as you practice with these, it will get a lot easier. And I will upload another video that will just go through different practice problems. So until next time, have a nice time. Have a nice night.